Alright guys, so our last technique of this chapter is something called logarithmic differentiation, and the first sentence that I have there, it's something that we use when it's a function that we don't really have any other method to use. So the example that we've got, example 1, 2, 3, the most common way we'll need to use it is when we have a variable raised to a variable, like x raised to the x. So if you think about what we've got, we have the power rule, and in the power rule we can take a variable based to a number, and in the exponential rules, we can take a number raised to a variable, but we don't have any rules so far that will take a variable raised to a variable. So we've got something called logarithmic differentiation. So I'm going to walk you through the steps, and then we're going to apply those steps to this particular equation that we're trying to differentiate. All right, so step 1 is you want to take the natural log of both sides, which is why it's called logarithmic differentiation. Now, I'm sure you're starting to realize by now, the way that this algebra works is basically there's almost anything that you can do to one side as long as you do it to the other side. So on this equation right here, we are going to take the natural log of y, and then we're going to take the natural log of x to the x. All right, so then step 2, now that we've taken the natural logs, like the left-hand side, nothing special is going to happen on the left-hand side, but that's not the side that we were worried about anyways. What's going to happen on the right-hand side, if you guys remember some of those logarithmic properties, if you've got the natural log and then you've got a power on the inside, remember one of our properties told us that you can take this power right here and move it out front as a coefficient. And so that's what's going to help us take the derivative here. So step 2, apply log properties. Okay, so the only log property that I can apply right here is the one I just talked about, taking this coefficient and then moving it out to the front. So the left-hand side stays the same. It's still the natural log of y. But on the right-hand side, I apply what I normally use as the third property of logarithms, which says if I've got if I have an exponent on the inside, I can move it out front as a coefficient. We actually just saw something kind of similar to that in the last set of notes. And then step 3 is we differentiate. We're going to have to differentiate implicitly because we do have a y mixed in there. So we are going to differentiate implicitly. So differentiating, remember, just like we've been doing for the last couple of days, means taking the derivative with respect to x of both sides. So we've got some brand new rules that we can apply here. We just learned the derivative of a logarithmic function, so we can apply it right here. So the derivative of the natural log of y with respect to x. Now, x is our variable of choice here, which means anytime we're using a different variable, we have to use implicit differentiation. We have to throw in that dy by dx when we're done. So the derivative of the natural log of y would be 1 over y. But then we multiply by dy by dx, because y is the nested function, and we have to multiply by its derivative. Equals, and then on the right-hand side here, we're going to do a product rule. So let me do a little side work. So u, the first function, is x. V, the second function, is the natural log of x. And then we have u prime, the derivative of x is just 1, and then v prime, the derivative of natural log of x is the one we just learned, that is 1 over x. So we can apply everything here using our product rule, so we crisscross, so x times 1 over x, well that just gives us 1. And then plus the natural log of x times 1, anything times 1 just stays the same, so this is just going to be the natural log of x. Alright, so now we are just about done here. Remember, our goal is always to get dy by dx by itself. So what I can do is I can multiply both sides by y. And when I multiply both sides by y, then the dy by dx part will just be all by itself. Alright, so we've got dy by dx equals, and then I have a y on the right-hand side. But now the last thing, preferably, I would like everything to be in terms of x, if it can be. So now instead of putting a y, we know from the original equation that y is equal to x to the x. So instead of a y, I'm going to replace it with x to the x, and then times 1 plus the natural log of x. So that is my final derivative. That is the derivative of x to the x. Okay, second example, we're going to do something really similar here. It'll go a little bit more quickly this time because we kind of know what the steps are. Steps are exactly the same. So we start by taking the natural log of both sides. So we have the natural log of y equals the natural log of x raised to the tangent x power, and then we can apply our log properties. So the tangent can come out front and then multiply by my natural log of x function. So I'm sure you've noticed with the right-hand side, there's always going to be a product rule involved because this power is going to come out front and multiply by my natural log function. Okay, so now I take the derivative of both sides with respect to x. The good news is, even if we're not the biggest fan of implicit differentiation, for this stuff, the left-hand side will always have the same derivative. It'll be 1 over y, but then since I need to do a little chain rule, I multiply by dy by dx, which is the derivative of the nested function. Okay, and then equals, again, let me set up my product rule over here. So the first function u is tangent. The derivative of u, the derivative of tangent, is secant squared. My second function is the natural log of x, and just like we've been doing, the derivative of natural log of x is a 1 over x. Okay, so for the product rule on the right-hand side, we crisscross, so tangent x times 1 over x. So we could write tangent x over x if you wanted to, and no, those x's cannot just cancel. And then plus, we crisscross here, natural log of x times secant squared x. All right, so we would leave that side just the way it is. Last thing to do to get the dy by dx by itself is to multiply both sides of the equation by y. That way we can get the dy by dx by itself, which is exactly what happens on the left. We get the dy by dx all by itself. But remember, just like the first example, we don't want to leave our function in terms of y if we don't have to. We'd like it to be all in terms of x. So we know that y is equal to x raised to the tangent x. And then we leave the rest of it in parentheses. And there is absolutely no need to simplify beyond this point, nor do I think there really would be much that you could do. Okay, last one of these. X raised to the 1 over the natural log of x. So first step, take the natural log of both sides. Second step, apply log properties. So on the right-hand side here, the 1 over natural log of x will come out front, and it will multiply by the natural log of x. And oh my goodness, this is wonderful. These are going to reduce down. My right-hand side is now just 1. All right, so what I have is the natural log of y just equals 1. Still, I go on to the same property that I had next, or the same step that I had next. I still take the derivative with respect to x of both sides. So same derivative on the left-hand side that I've had for all these problems. We've got 1 over y, and then times dy by dx. Well, the derivative of the right-hand side is just 0, because that's a constant. So even when I multiply both sides by y, which I'm going to write out that step anyways, but even when I multiply both sides of the equation by y, I am just going to get a 0. So I want to show you this, because this is telling me that the derivative function is 0. So if the derivative is 0, that must mean that the original function was constant. So if you guys get a second, plug this in. You'll show that you get a constant function, which is why you end up with the derivative of 0. All right, so that's the first reason that you can need to use logarithmic differentiation, if you have a variable in the base and a variable in the power. There are also situations, like we said, where the function is just nasty, and it would be, let me flip so I can have an example in front of us. Taking the derivative of these would be possible, but for this one, we would have a product rule, a chain rule again, and a quotient rule. Like this is nauseating to think about doing that. So the logarithmic differentiation is available for this situation as well. So let me just write up on the top, because we're going to use all of the logarithmic properties, not just the ones that we used on the front. So the first one says if we've got the natural log of a product, a times b, we can split it as the natural log of A plus the natural log of B. Second property says if we've got the natural log of a quotient, we can split it up and do subtraction. And then the third property is the one that we were just using. And that's if we have the natural log of A to the M, we can bring the M out front as a coefficient. So we already used that one, but just so you've got those in front of you, just to keep them in mind. So we still use the exact same steps that we used before. We're going to take the natural log of both sides. So natural log of the left equals natural log of the right, this whole thing right here. So now the first handful of steps are going to be more like algebra pre-calc stuff than really any sort of calculus. So the first step was to take the natural log of both sides, and then remember the second step is to apply your log properties. So this equals, so applying log properties, first hopefully you notice I've got a quotient here, so I can apply property number 2. So I write the natural log of the numerator minus the natural log of the denominator. Okay, and then we can continue to simplify using these rules. So this one, for example, I've got a product. So I can apply this property right here. So equals the natural log of x, the first piece, and then plus the natural log of, and I'm going to write this as a power, x squared plus 1 raised to the 1/2 power, because that's the last thing that I will apply. And then minus the natural log of x plus 1 to the 2/3. All right, so I have all of these pieces kind of separated out. The last thing I'm going to do is apply this third property where I have this power right here, this power right here. I'm going to throw them out front as coefficients. Okay, so that's where I'm at so far. So after I took the natural log of this right-hand side here, I was able to use all these properties to get it actually quite a bit simplified down. So now don't forget my left-hand side is still the natural log of y. So that's my second step. It just took me a while to get through my second step this time. Normally the second step was just throwing a power out front here. My second step is to apply log properties, and then I differentiate implicitly. So I'm going to differentiate with respect to x. So take the derivative of the left with respect to x. That derivative has not changed for this entire lesson. And then take the derivative of the right-hand side with respect to x. Okay, so just like on the front, this derivative is just a 1 over y times dy by dx, and then equals, then I start to take the derivative of these pieces right here. And now taking the derivative of these pieces, because natural log is a wonderfully easy derivative, taking the derivative of these pieces is so much easier than taking the derivative of these pieces. So derivative of natural log of x, just 1 over x, and then plus, I've got a constant here, so remember the constant multiple rule says you can just let it kind of hang out front. And then for this piece, I have to use a chain rule. So the derivative of natural log of x is 1 over whatever. So I write 1 over, I leave my x squared plus 1 in place because I'm doing a chain rule. But then because, like I said, I'm doing the chain rule, I have to multiply by the derivative of the x squared plus 1, which is 2x. And then minus, again, constant multiple rule says I just let that 2/3 hang out front. And then I multiply by the derivative of this piece right here. Again, chain rule says when I take the derivative, I leave the x plus 1 in place, and then multiply by the derivative of x plus 1, which is just a 1. All right, so now I have all of my pieces here. I'm going to simplify, clean up just a little bit. So this equals 1 over x, and then plus, first of all, these 2's will cancel, and I will have x over x squared plus 1, and then minus 2 over, and I can distribute this 3, and I'll have a 3x plus 3. All right, so that is my right-hand side, totally cleaned up. The last thing that I can do, just like I did the previous problems, is I multiply both sides by y so that I can get the dy by dx by itself. So the dy by dx is now all alone on the left-hand side. But remember, just like in the previous problems, we don't want to leave this as a y. We want to replace the original function. So instead of y, I'm going to write x root x squared plus 1, and then over x plus 1 to the 2/3, and then times this entire beautiful quantity. So if we had chosen to do this out the long way, you know, product rule, quotient rule, chain rule, and all sorts of other things, this is the same answer we would have got. Probably not in the same form. We would have had to simplify it a little bit, but it's so much easier to do natural log derivatives than it would have been to do product rule, quotient rule, double chain rule, and all sorts of other fun. All right, last one here. Same thing. We're going to take the natural log of both sides. So natural log. So we've still got, the natural log of y. We'll come back for that in a moment. And then we can start applying properties on this right-hand side here. So first we've got a quotient. So we can take the natural log of the numerator. And then minus the natural log of the denominator. And then this piece right here is a product, so I can use the first property that we wrote down to split that up. And plus okay, and then I apply the third property, and I take these exponents here, and I move them out to the front as coefficients. Okay, so bring this back down. So that was my second step, just applying all of these properties. My third step is to take the derivative of both sides with respect to x. Okay, so left-hand side, exact same derivative it's been for all four problems so far. Just 1 over y, but then because I have a nested function of y, I multiply by its derivative, equals, and then these are just nice and easy derivatives. The 4 stays out front. The derivative of the natural log of x minus 3. First of all, I leave the x minus 3 nested, and then I multiply by its derivative. The derivative of x minus 3 is just 1. Plus, the derivative of natural log is 1 over. I leave the x squared plus 1 nested in place, and then I multiply by the correction factor. The derivative of x squared plus 1 is 2x. Minus, I leave the 3 out front, using the constant multiple rule. Derivative of natural log is 1 over. I leave the 2x plus 5 nested in place. And then finally times the derivative of 2x plus 5. It's a linear function, so its derivative is just 2. Okay, so clean up this right-hand side. So for this term right here, oops, I guess the 1 is included there as well. I get 4 over the quantity x minus 3. And then plus this next quantity right here, I can write 2x over x squared plus 1, and then with this one I've got a couple constants to play with, so I can put a 6, the 3 times 2, over 2x plus 5. So that is my right-hand side all cleaned up. So here's my left-hand side, haven't changed that yet. So same final step as all the other ones. I multiply both sides by y, and then I replace the y with the original function. So on the left-hand side, dy by dx is now by itself. I replace this y right here with my original beautiful function. Okay, so there is, again, just another gorgeous derivative. And last thing, in case you're wondering, any time that you're supposed to be using logarithmic differentiation, especially on ones like these on the back page, I would tell you. All right, so don't just decide that you're going to do logarithmic differentiation. You will be explicitly told. All right, that's it.